Okay, so example 2. All right, this is a pretty easy one as well, so we're just going to snip the whole thing. This is just plug and chug, right? So if we just have f of x being 3x squared plus x minus 5, evaluate each function. We're just going to plug in we're going to plug in -2 for x, we're going to plug in 0, we're going to plug in 4, we're going to plug in 1/2. Okay, that's it. We're just plugging in these values for x and solving, doing the arithmetic at that point. Piecewise defined function. So this is a good one to talk about. And okay, so I do a lot of talking and teaching, believe it or not, right? And so if I repeat a story, I'm sorry, but this is important to me because when I was in undergrad, I was a horrible student. Okay, my first year, I remember taking college algebra, and I mean, heck, it was probably even in high school. I remember getting to piecewise defined functions, and I remember thinking, okay, so these functions, they don't look like anything that I'm used to, and I'm not even gonna rub two brain cells together to figure it out, and I'm just gonna hope that there are not a lot of piecewise defined functions on the test. Okay, that was me as a first year college student, and now look at me, I'm teaching this stuff, right? But it's really not that hard. Okay, so what we're going to do, a piecewise defined function, it looks different, okay, but it's not really so different. And here's what I mean by that. It is basically it's a cheat, right? You know, do you ever have your professors? They're like, there's 5 questions on this quiz, okay, but question 1 has 4 parts. Question 2 has 3 parts, right? So it's really more than 5 questions, isn't it? That's kind of how the piecewise defined functions are. Piecewise defined functions are defined as one function, but really have multiple functions. Okay? So what you do is you look at whenever you are evaluating at a function is you look here. These are essentially the domains. Oh no, we have to talk about domains today too. These are the domains of a function, of this function. So the function 39 has the domain from 0 to 2, including 0 and including 2. So what you would do is, so this is c of 0.5, okay? So 0.5, does 0.5 reside here, or does it reside here? Okay, well obviously it resides from 0 to 2. So c of 0.5 is simply 39. I'm just going to write that. C of 0.5 is equal to 39. Okay. Well, now C of 2. Okay. 2, does 2 reside here, or does 2 reside here? Okay. Well, it's tricky, so you want to be careful here, but it would reside here, right? Because this says or equal to 2. Okay. So C of 2 would also use that function, which is simply 39. Okay, and 4 has to be just difficult, right? Is 4 between 0 and 2? No. Is 4 greater than 2? Yes. So I'm going to use this equation. So C of 4 is equal to 39 plus 15, 4 minus 2. Okay, I'm plugging in the 4 for the x, right? So 4 minus 2, well, that is 2. 2 times 15 is 30. 30 plus 39 is 69. So C of 4 is 69. Right? And that's a piecewise defined function. Net change, another thing I'm just going to snip and chat about. Okay, so example 4, finding net change. So we're going to let f of x, again, that's the name of the function, f of x is equal to x squared. So we're going to find the net change in the value of f between the given inputs. And did we actually get the definition of net change? Oh, probably should snip that too, huh? There we go. Okay, so if we're looking at this definition, the net change is in the value of f as the input changes a to b, where a is less than b, okay? So keep in mind, a has got to be less than b. So it's given by the function of b, the function of the larger number, minus the function of the smaller number, okay? So we look at a here. What's the large number? Well, it's 3, right? So we're going to say f of 3 minus f of 1, the smaller number. Well, 3 squared is 9, 1 squared is 1, so that the net change is 8. Okay. Here, example B, well, what's the larger number? Well, it's 2. The smaller number is negative 2. So we'll say f of 2, the larger number, minus f of negative 2, the smaller number. Well, that's 4 minus 4, so net change is 0. Okay, and we'll talk about net change a lot more in the future. This is just a quick crash course in it. It's the function of the large number minus the function of the smaller number. That's it. Okay. The next example, I believe, is very heavy in the arithmetic. But it's really just a practice in, keeping your ducks in a row. And it's another one I'm just going to snip because it is really just plug it in and solve from there. Solutions. Nothing to add there. This is huge, humongous. All right, so I might have halfway lied about function being the biggest thing. The domain is probably the biggest thing. Maybe not lied, obviously, but just a little incorrect. Okay. So let's see if I need to snip anything else here before I need to talk about it. No. Okay. I did that because I don't want to get pissed off and shut down again. Anyways, so recall that the domain of a function is a set of all inputs for the function. The domain of a function may be stated explicitly. For example, if we write f of x is equal to x squared, 0 to 5, this means that the domain is a set of all real numbers x for which x has to be between 0 and 5. Okay, the domain tells us what numbers that we are allowed to use. Okay, if the function is given by an algebraic expression and the domain is not stated explicitly, then by convention the domain of the function is the set of all real numbers. Okay, so if you are not given a domain for the equation, like this, if it doesn't look like this, then it's presumed that the domain is all real numbers. And we've seen, have we seen? Yeah, so we've seen this equation. So there is no domain given, so the presumption is that the domain is all real numbers. That what I mean by that is that I'm allowed to use every single possible number you can imagine. Okay, now why would we want to restrict a domain? Now obviously, here in a vacuum in our math classes, we want to restrict domains for fun, right? But in the real world, you might need to restrict domains for other things. Like for instance, if let's say we shoot a rocket, okay? Okay, we shoot a rocket, it goes up, it goes down, and let's say it hits the ground in 10 seconds. Okay, so it hits the ground in 10 seconds, and this function, the function of this graph, okay, we're just going to call alpha. So it's just alpha, okay? That there's no x squareds, x cubes. We're just going to call it just plain old alpha, okay? So the domain of f of x here, and honestly, I don't think I need to do anything like that. The domain of f of x here is from 0 to 10. Why? Well, think about it. If my little toy rocket goes up and down, and I want to know what is the height of the rocket, at different stages of time, this would be 5 seconds, so on and so forth. Well, at -3 seconds, well, that doesn't exist, does it? That's outside the domain, right? I did not shoot this rocket. I cannot shoot this rocket off -3 seconds ago, right? Same thing with 15. Okay, well, at 15 seconds, it's already hit the ground. Okay, now you could say, its height is 0, that's fine. But, for just figuring out the actual heights and the height being, where this red and green line intersect. For like just finding the height of the rocket, it's got to be between 0 seconds and 10 seconds. So we want to restrict the domain of this function from 0 to 10. You know, we can include them, that's fine, okay? From 0 to 10, we want to restrict the domain of this toy rocket's trajectory from 0 to 10. And then we can find the height. So okay, that's why we need to restrict domains. But again, in this class, I mean, there are, trust me, there are plenty of word examples if you want them. But in this class, we mainly just restrict domains just for the fun of it. All right, all that stuff is good. You can read it. All right, before we begin the last thing, I believe example 7 would be the last part of this. I want to talk about the domain Bible. Okay, so I'm going to try to actually just write this out with my handwriting, but writing on a tablet, being left-handed, it might be ugly, so I might just pull out the typing. Okay, but this is the domain Bible. If you have not taken a single note up until now, this is what you need to write. Okay, so this is the domain Bible. Okay, so first thing we're going to say is that the domain of a function, if you can see TION, is always all real numbers. Okay. Another way to write all real numbers, and I kind of ran out of room, would be from negative to infinity to infinity. That's another way to write it. But I'm just going to write that funny looking R, and again, if you want to write it, it's these 2 lines and the R like that. Okay. So the domain of a function is always all real numbers, or again, that's negative infinity to positive infinity, unless and actually I didn't really need this to be 1. Okay, so the domain of a function is always all real numbers, unless number 1, this is what I needed a number, unless number 1, we have a variable, we have and I mean, denominator. This looks like squiggles, I know, but it's denominator, right? Unless number 1, we have a variable in the denominator, and number 2, let's just write we have. I don't like putting those little dots. We have a variable n, and I don't want to put in a radical. How should I put this? And all right, we'll do it. Even indexed, and that is promise my handwriting is way, but like I take a lot of pride in my handwriting. This is just awful. But we have a variable and an even indexed radical. Okay, and we'll see examples of that coming up. Okay, so this is the domain Bible. You need to have this memorized 100%. Write it down. If you can't read it, then watch the video and rewind it and hear my words, hear my voice rather. Finding the domain. Okay, so this problem, find the domain of each function. A, 1 over x squared minus x. Okay, so this is going to violate, let's see what we'll do, put it up here. This is going to violate my first rule, right? Again, the domain of a function is always all real numbers unless, number 1, we have a variable in the denominator. Number 2, we have a variable in an even indexed radical. Okay, so this we have a variable in the denominator. So we've hit the unless criteria. Okay, so we need to what we need to do here is we need to figure out what makes the denominator equal to 0. Okay, and in order to figure out what makes the denominator equal to 0, I'm going to set the denominator to equal to 0. Okay, and then of course I factor out an x. I'm left with an x minus 1 is equal to 0. And therefore, solving what's written in blue, if I solve what's written in blue, then it is x is equal to 0 and x is equal to 1. That's what's solving in blue, okay? That's not the domain. The domain is not 0 and 1. That's just solving to make, x squared minus x equals 0. So what this tells me is that for this particular problem, for A, the domain would be x cannot be equal to 0 and x cannot be equal to 1. Okay, that would be the domain. The domain is every number except 0 and 1. Because if I plug in a 0 or a 1, if I did f of 0, I would get a 0 in the denominator. If I did f of 1, I would get a 0 in the denominator. Okay, and we're going to do C, and then I'm pretty sure we'll have to call it. We're already over time. I knew it'd be a little bit long. Okay, but B. Okay, so this is g of x is equal to 9 minus x squared. So this violates my second criteria, right? We have a variable in an even indexed radical. So when I say index, I'm talking about the number right here. Obviously, if there's not a number there, we know that it isn't applied to, okay? But an even index radical, right? 2, 4, 6, 8, 10, things like that, right? Cube root, well, that's not an even index radical, so that doesn't matter. An even index radical, it's pretty self-explanatory. I'm not going to say it again. Okay, so when I'm looking at this number, okay, 9 minus x squared. So what I have to do here is I have to recall that the number inside my radical, okay, what can it not be? Well, it cannot be a negative number. It can be 0, and it can be any number greater than 0, okay? So what I'm going to have to do is I'm going to have to take this 9 minus x squared, and I'm going to set it equal to greater than or equal to 0. Okay, so what I'm doing now is figuring out, okay, my my solution, my domain has got to be greater than or equal to 0. So then when I solve for this, all right, so this becomes what? Negative x squared is greater than or equal to negative 9, and therefore x is less than or equal to, and then we take the square root, so plus or minus 3, right? Okay, now again, that's not the domain. That's not the domain. What that's telling me is that this is going to now be, and that's unfortunate, but this is now going to be the walls of my number line that we did in 1.7. Okay, and then you have your wall at -3 and your wall at 3, and then you plug the values in just like we did in 1.7 or at the beginning of this lecture. But since it's a 3-part lecture, it'd be in the one of 3 parts, right? And then you would get your solution set, and it would be -3 to +3. But I'll let you figure that out. Let you get there yourself, or look at the book, right? And last thing, I think I just have to snip this last thing, and then we'll be done. Yeah, there we go. -3 to +3. Using the method of section 1.7. Yeah, so The last thing is, I think, is just a ways to represent the function. Yeah. And I'm just going to snip this. I'm not going to talk about it, but it will be in the notes. And that concludes this lecture.